So, this is the last in this series of talks in which the general theme is the power of a small list of ideas. Forefront was the idea of equality. Then there was the idea of using symbols such as x, and then there was the idea of using units, mass, length and time. And as we have stressed that it was the use of units that created modern day science. It allowed things to be measured and given a numerical value. So, the idea of units has been mentioned in isolation. We have talked about the length in something when we were discussing geometry. Then we introduced mass when we were introducing Newton's law, and we introduced the time when we are looking at the time evolution of a particular system. What I would like to do now is to show the great power which is present in the constants themselves, the units themselves, and how by understanding the presence of these units you can draw various significant conclusions. In certain areas of engineering, people introduce additional units. So, what I will do is I will show how using a certain convention, in the way we would look at it, the additional units are not necessary for what we do. So, let us look at the meaning of these things. So, the mass is a measure of the amount of matter, roughly intuitively. Length is the measure of the extent of something, and t is the way in which things change as we look at them at different periods. And we know about change in our everyday life. Things are constantly changing. The laws of physics, as written down, try to capture and give a reason for the change. So, let us look at an example. Let us look at the force. The force is the mass into acceleration. The acceleration is the rate of change of velocity, and the velocity is equal to rate of change of position. So, these things you see we can then relate to what we have on this side. So, let us look at force. Let us start with the velocity. So, the velocity v is the change of position. Position is a length. So, for example, if I have a coordinate system like this, the position p is given by this length. So, it is related to a length, and then the way it is changing is time. Rate of change is time. So, this is by t. So, the dimension, you introduce the idea for dimension, this is the dimension of mass, you write m, length L, time. These are the dimensions. So, the velocity we can add on this list. The velocity is length over time. then the acceleration, I will put this up here. So, the acceleration is a change of velocity. So, the acceleration, if I call that A, acceleration is the rate of change of velocity, that is the velocity divided by time, which is the same thing as length by. So, these simple equations are extremely useful. So, let us go through this again. So, we have said the acceleration is the velocity divided by time, but the velocity is length divided by time. So, there is 2 factors of time underneath. I have written that as t squared. So, the acceleration has this form, A is like this. Then the force F is equal to the mass and the acceleration, which is L t minus 2, right. So, we can put them on our table. So, in our table, so this is then force and this is acceleration. And finally, we have the idea of energy. Energy means that if you have a force and you are doing you're going against the force or going with the force, that is a measure of energy. So, the energy is force into distance, which is L, which is equal to, from here, m L squared minus 2. So, this is the first step. So, this is the dimensions when we write down an equation in physics, then it is a requirement that the left hand side and the right hand side have to have the same dimension. Okay? So, that is a requirement. So, any physical expression, equation must have the same dimension. On both sides. You see. And the reason for that is an equation is something which does not depend on the units you choose. So, suppose someone writes down an equation using inches and pounds, someone else writes kilometers and grams. This equation has the same structure, right. What will happen is the numerical value of m and the force will change. They depend on the units. So, that when we are dealing with the real world, units are essential. Without units, one cannot make progress, one cannot measure things properly. But the equations themselves should have the property that if I divide one side of the equation by the other side, what I get should be independent of dimensions. Okay? And this is the key idea. Right. So, let us look at Newton's law to check this thing out. You see, Newton's law was force is equal to mass into acceleration. Right. The force we found was m L t to the minus 2. This is this part, and this part was mass L minus 2. Right. So, the force at this balance, and the reason is that that is the way we have said that the force is the mass into acceleration. So, there is not quite trivial. That is, by construction we have got this result by demanding that the force dimension is nothing but mass into acceleration. So, there is no surprise in getting this result. So, let us look at an application. But as an application, let us try to see if we can get Bohr's formula for the hydrogen atom by using dimensions. In order to do this, what we have to say that we want an expression for the energy E. This is the energy required, and we have to say what does the energy depend on, what is the physics, you have to put that in. So, you say that this energy depends on E, the electric charge, it depends on m, the electron mass, and it depends on h bar, Planck's constant. It does not depend on anything else. The reason is that in the Bohr type of model, the radius of the thing is something which is fixed, which comes out from all of these things. The basic thing is there is electromagnetic interaction, electrostatic interaction, that is why E has to be there. The interaction acts on a mass, that the mass has to be there, and the whole system is governed by quantum theory. So, h bar has to be there. Okay. So, those are the basic units. So, what do? We say that some combination of E, m and h bar have to come together to give you the dimension of energy. So, let us try and do that. So, what we have is you want the energy which has dimension. So, the left hand side, this is this side, has dimension of energy. Energy is m L squared t to the power minus 2, right. And on the other side, this has to be the right hand side, has to be the dimension of E to the power of say alpha 1, the dimension of m, which is to the power of alpha 2, and the dimension of h bar to the power of alpha 3. And these three, alpha 1, alpha 2, alpha 3, are certain things which we will determine, so that this gives you this dimension. So, to proceed, we have to find what is the dimension of E. That is, we want to express the dimension of electric charge in terms of m, l and t. How do we do that? To fix this, we use the fact that E squared over r is energy. Okay. So, this is the Coulomb energy. When you use that, then we have selected a system of dimensions in which the Coulomb energy does not have any constants here, right. Then if there was a constant, it would be a bit different, but you just have E squared over r, and these are called the electrostatic units. So, for the electrostatic units, this is okay. So, this means that E squared dimension is energy is m, we just wrote down energy, m L squared t to the power minus 2, and then it is multiplied by L. So, that means E has the dimension of m to the power of half L to the power of 3 over 2 t to the power of minus 1. Now, this systematic use of dimensions for analyzing the physical problem was started by many people, but Fourier was one of the earliest people. And then later James Clerk Maxwell and William Thomson in around about 1874, round about there, they did this systematically. So, this thing we have found E and we write it down, which is m to the power of half L to the power of 3 over 2 t to the power of minus 1. So, this thing we have done, right. Then m is easy. Now, we have h bar. H bar is energy into time. So, that is energy is m L squared t to the power minus 1 into t. So, this is equal to m L squared minus 1. So, h bar is then equal to m L squared t to the minus 1. So, what we have done is the left hand side is we want it to be an energy, the right hand side from physical arguments. This is where our insight into the system shows up. From physical arguments, we have said it is going to be a function of E, m and h bar, and they are raised to some powers which we do not know, and the powers have to be chosen so that the dimensions on this side are equal to the dimensions on the other side. So, we want to match dimensions. So, problem is choose alpha 1, alpha 2, alpha 3, so that the dimensions match. So, let us do that. So, e to the power of alpha 1, the dimension of that is m to the power of alpha 1 over 2, L to the power of 3 alpha 1 over 2, t to the power of minus alpha 1. M to the power of alpha 2 is m to the power of alpha 2, and h bar to the power of alpha 3 is m to the power of alpha 3, L to the power of 2 alpha 3, t to the power of minus alpha 3. Okay. So, when I write this down, I have to take the product of these three things. So, it is a combination, it is not adding them, you are putting them together. So, you look at the product of these three terms, and what do we get? We get m to the power of alpha 1 over 2, L to the power of 3 alpha 1 over 2, t to the power of minus alpha 1 multiplied by m to the power of alpha 2 multiplied by m to the power of alpha 3 So, we put them together. So, this is then m to the power of alpha 1 over 2 plus alpha 2, alpha 1 2 by alpha 3 plus alpha 3, alpha 2, alpha 1, alpha 3, L to the power of 2 alpha 3 plus 3 alpha 1 over 2. So, m, 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 L, L, and then t to the power of minus alpha 1 plus alpha 3. Now, these factors should match what we have here. So, what we require then is alpha 1 over 2 plus alpha 2 plus alpha 3 should be equal to 1, 2 alpha 3 plus 3 alpha 1 over 2 should be equal to 2, and minus alpha 1 plus alpha 3 should be equal to minus 2. Right. So, then they match, right. So, what we find from here, the last one, what we find from this expression is I can make this plus. So, what we find is that alpha 3 is equal to 2 minus alpha 1. Okay. So, let us look I'll write them down here. So, we have alpha 1 over 2 plus alpha 2 plus alpha 3 is equal to 1, 2 alpha 3 plus 2 alpha 1 over 3 alpha 1 over 2 is equal to 2, and we found that alpha 2 is equal to 2 minus alpha 1. Right. So, if I substitute in here, then I get, so use this, so this is 1, 2, 3. So, use 3 in 1, then we get alpha 1 over 2 plus 2 minus alpha 1 plus alpha 3 is equal to 1, and 3 alpha 3 plus 3 over 2 alpha 1 is equal to 2. We find that from here, right, there is a thing from here, I subtract, so I get 2 minus half alpha 1, right, 2 minus half plus alpha 3 is equal to 1, right, and from here I get 3 alpha 3 plus 3 over 2 alpha 1 is equal to 2, right. So, what I can do is I can multiply this whole thing by 2. So, I get 4 minus alpha 1 plus alpha 3 . So, I multiply this equation by 2, I get that, and this equation I am I multiply by, I needn't, I could have just, yeah. Okay. So, I could have just simplified the thing. I could just, from here, I can write 4 minus 2 alpha 3 is 2 plus alpha 1. So, alpha 1 is equal to, I take the 2 on this side, 2 minus 2 alpha 3. Right. So, 4 minus this, I then have the 4, have this, I have taken that on the other side. So, then alpha 1 is equal to, I subtract, I get this. I substitute that in here. So, I get 3 alpha 3 plus 3 over 2 into 2 minus 2 alpha 3 is equal to 2. Okay. So, that means that you have 3 alpha 3 plus 3 minus I have made a mistake somewhere. This is 6, this is 3. I have made a mistake somewhere. It is just too complicated to go back. So, what if I messed up with the algebra somewhere. So, what we expect to get is e to the power of alpha 1, m to the power of alpha 2, right, h bar to the power of alpha 3. So, if you do it right, and then you get alpha 1 is equal to 4, alpha 2 is equal to 1, and h alpha 3 is equal to minus 2. That is what we should get. Right. So, I think the procedure I have outlined is absolutely right. So, but the procedure, if you just do it a bit more carefully, what you will end up is getting this, and you find that then E is equal to e to the power of 4 m over h bar squared. Now, I can tidy this up, and we can include that at a later date. So, that is the procedure, right. So, the procedure is, I have complicated the thing procedure by doing it in a certain ordering, but the idea is extremely straightforward. I have indicated how E, m and h bar can be related to the fundamental units m, l and t. Once I have done that, then the expression, this expression has to balance this expression, and so that means the power of m I get has to be 1, the power of l I get is 2, and the power of t is minus 2. Those I have to get, and once I put that in correctly, then there is no choice, and one can immediately get the result which I have written down. So, I will give one more example just to clear the air, and then maybe I will do this again, so that this time I will do it very slowly, and hopefully we will get it right, so that you can edit and put in the right one. So, I will redo this calculation again. Okay? So, what we want to do, starting again. So, what we want to show is the energy of the hydrogen atom, which is m l minus 2 force and resistance. This thing is some e to the power of alpha 1, m to the power of alpha 2, h bar to the power of alpha 3. And the reason we have picked this is because we know this is a quantum system, the electrostatic forces are there and they act on a mass. So, the charge has to be there, the mass has to be there, and it is a quantum system. So, this has to be there. Then we found the dimension of E from this expression, and this is energy. So, this is m L squared minus 2, and if I multiply this by r, so E squared has a dimension of m L cubed t to the power of minus 2. So, E has a dimension of m to the power of half L 3 over 2 t to the power of minus 1. So, this is good. So, the m has the dimension of m, and h bar is erg's energy into seconds, and the energy is m L squared t to the power of minus 2 into t. So, this I think we had right, m L squared t to the power of minus 1. Okay. Right. So, what we will do now is we will choose one of these units to be equal to 1. So, choose alpha 2 is equal to 1. Okay. If then alpha 1, alpha 3 will look after, everything will be looked after. So, once I have chosen that, then this thing according to this formula here is m to the power of half alpha 1 L to the power of 3 over 2 alpha 1 t to the power of minus alpha 1, then this is multiplied by m, and then it's multiplied by h bar, which is m to the power of alpha 3 L to the power of 2 alpha 3 t to the power of minus alpha 3. Okay. So, that is the expression now, where I have made a choice, and if alpha 2 is not equal to 1, in this whole business there will be a m factor which will come out to make it work. Okay. And so, I know m is here, so I have made that thing right. So, this is then equal to m to the power of half alpha 1 plus alpha 3 L to the power of 3 over 2 alpha 1 plus 3 alpha 3 and t to the power of minus alpha 1 plus alpha 3. Half like this, 3 over 2 like this, like that. So, now what we have is I want half. So, there is a m already, right, which is here m. I have just looked at this, and so what I want is half alpha 1 plus alpha 3 is 0, right. Then I want 3 over 2 alpha 1 plus 3 alpha 3 is equal to L is 2 and t to the power of minus alpha 1 plus alpha 3. So, this is minus alpha 1 plus alpha 3 is equal to minus 2. So, basically what we have is so this thing. So, what we have is then alpha 1 plus alpha 3 is equal to 2. So, alpha 3 is 2 minus alpha 1, right, and then we have something here. I do not know what rubbish I am doing. Alpha 3 is equal to 2 alpha 1, and this is equal to minus half. From here we get alpha 3 is equal to minus half alpha 1. So, this is minus half alpha 1. So, 2 minus alpha 1 minus plus minus half alpha 1, 2 minus alpha 1 is minus half alpha 1. So, you have 2 is equal to, I take the alpha 1 is half alpha 1. So, alpha 1 is equal to 4. Right. So, alpha 1 is equal to 4, which means that you have E fourth and H 3 alpha 3 is minus half alpha 1. So, what we have then is that e to the fourth alpha 2 we've chosen to be 1, and alpha 3 is minus half, and this is equal to minus 2. Right. Okay. So, what we have succeeded in doing eventually is to show that this rather cumbrous procedure, it is simple and you have to do it a bit carefully. By just matching the requirement, you get the Bohr structure, and the key input which we used was that the variables chosen were guided by physics principles. So, the idea then is the use of the units is not just something which allows you to convert physical measurements to numbers, but they are present in the structure, and by exploiting that structure you can actually derive specific expressions. So, in this case, without using any quantum theory or any detailed dynamics, just from the fact that you have to construct the energy out of the variables, you have a result. So, the input is the physics input, and once the physics input is there, you get these kind of results. So, I hope these things have illustrated the great power of thinking in simple ways, and the use of dimensional analysis for finding out unknown areas of science and predicting the dependence on variables is it's an extremely powerful tool which is used constantly, especially by engineers. It's a very, very useful tool for having a first look at a problem. I hope these lectures have opened your eyes to possibilities and suggested to you that sometimes one can understand fairly complex systems by using rather simple arguments. Thank you. I don't know what went wrong first time.
I got it.
Yeah.